there are quite a lot of applications of the projection theorem. We're going to talk about some specific ones. So here are two that we're going to look at specifically in this class. This one we're going to look at in this lecture. This one we're going to find later when we actually look at controllability. But curve fitting problems. So we're going to start with linear regression. Suppose we have some data, x and y, x values and y values. So x corresponds to y, and so we have n data values that we've collected perhaps from some experiment. Okay, and so what we'd like to do is we propose the hypothesis. That is, this is our hypothesis. Y is equal to mx plus b. We want to assume a line. So this is linear regression. We're trying to get a line. Now, if the actual data fits this, then for each value y and each value x, they should satisfy the relationship for the line. And we can then define the error, which is the difference between this and this. Okay, so the error value should be 0 for each data value if it fits exactly. However, if there's noise or inaccuracies, the errors will be non-zero. So we can parameterize now the hypothesis this way. The error is equal to the y values minus this row times this column is mx1 plus b. Okay, and so we can stack the data into this matrix equation. This is the values of y stacked into a matrix. X values are put into this matrix along with the values of 1, and then m and b are the same for all. So each row of this matrix basically corresponds to a line like this equation here. Okay, so in this case, m and b are our unknown parameters. Y and x we know. Those are the values that we got by experiment. Okay, and so what we would like to do then is to fit the data. Now we know that the least square solution to this problem is that. So we're looking for p. P is equal to x pseudo inverse times y. Okay, and we'll look at some specific examples of this when we get to our practice problems. Okay, but so that's the solution. That's the least square solution to this. That gives the best slope and intercept for the given data. Okay, suppose that we have, for example, some data, and we do our linear curve fit like we just looked at, but we find that the data doesn't fit a line very well. So we can see it's too curvy, and the curve is too predictable in a sense. So then we might consider another hypothesis. So instead of considering the linear hypothesis, we consider this quadratic hypothesis. Okay, so then we again parameterize the hypothesis and stack the data. So we would say y is equal to x1 squared a2 plus x1 a1 plus a0. And again, so that's basically this equation for each data value. Okay, so again we have y is equal to x. Notice the x here is different than what we had before. We have this additional column, and the p is different in that there's an extra term. So before there were only 2 unknowns, now there are 3 unknowns. Again, we can solve this problem by taking p is equal to the pseudo inverse of x times y. Okay, we'll talk more about the pseudo inverse later, but this is the solution to that problem. We can also do some other regressions, nonlinear regressions. So suppose we want to find the best fit for a function like this, that y is equal to a function of x, where we have c and b are unknown coefficients. How would you parameterize this equation? How would you set it up so that you can solve this using the same kind of approach we were using earlier, that is, setting it up as a linear algebra problem? So notice that this is not a linear problem, right? I have x squareds here, but I can set this up so that I get a linear algebra problem. Okay, this becomes a linear algebra problem. So how can we set this up so that we get a linear algebra problem? As a hint, one thing you can do is take the natural log of both sides of this equation. That gets rid of the exponent. Okay, well, I'm not going to actually solve this for you. I'll let you think about it, but this is a further application of the projection theorem.